Hi, everyone, and welcome back to Organic Chemistry on YouTube. Today, we're going to be talking about E2 reactions and the important stereochemical relationships that are needed to promote one of these reactions. Here are the basics. First, the typical example of a molecule that can undergo an E2 reaction is a hydrocarbon with a leaving group attached. This can be an alkyl halide. This can be a protonated alcohol. There are a lot of options here. And with a base, this will form an alkene. It typically needs to be a strong base. So instead of the alcohols that I've shown as an example for the E1 reaction in the previous episodes, what you need is something like an alkoxide. An example is methoxide shown here. These reactions are concerted and stereospecific, and there needs to be a 180-degree relationship between the acidic proton and the leaving group. So here's an example of the mechanism for this reaction. Okay, so this is bromobutane, and it can undergo a reaction with sodium methoxide and methanol to afford the following product. And it's the only product that's formed is this trans 2-butene. So this is one defining feature of E2 reactions. You only get one stereoisomer, not a mixture of the cis and trans 2-butene in this reaction. And here's why. The first step of this reaction is that this base, sodium methoxide, and I'm actually going to get rid of that sodium and put that just in blue. The sodium, remember, is just a counter ion. It's just to balance the charge on the CH3O, which is minus. The CH3O is the strong base. And the two hydrogens that I've shown here are going to be the ones that could be deprotonated. But we have to make a decision as to which one of these two will be deprotonated. Here, there's a difference, and it has to do with the required stereochemical relationship of these two protons. So what I'm going to do is I'm going to show a Newman projection looking down this bonds here to illustrate this point. Okay, so here's the Newman projection. As I mentioned earlier, the molecule and this reaction requires a 180-degree relationship between the acidic proton, which I'm underlining here, and the leaving group, which is bromine. So specifically, this hydrogen that I'm underlining here is the only hydrogen that can be deprotonated for this reaction to work. So when this molecule is deprotonated by methoxide, it takes specifically this hydrogen. It moves the 2 electrons from that carbon-hydrogen bond to the hydrocarbon framework, forms a pi bond, and kicks out the carbon-bromine bond all at the same time. The fact that these bonds are breaking and forming at the same time means that the reaction is concerted, and the fact that the stereochemistry of the reactant, that is this alkyl bromide here, dictates the stereochemistry of the product. That makes this reaction stereospecific. So when you show the arrows following these arrows, we can draw out the formation of the product, which is just the trans 2-butene. And if you look, the hydrogen that I'm underlining in green is here, and the other hydrogen that I'm underlining in green, double underlined there, is here. Right, one is a wedge, one is a dash. While those carbons are sp3 hybridized, that stereochemistry remains in the product here. Let's look at another example. So suppose we had this cyclohexane. It's really important in cyclohexane problems to draw them as a chair and not as the planar version that you see here. So converting this planar version of cyclohexane into a chair, so if this molecule is reacted with hydrochloric acid and water, the alcohol that we show here, because that's the most basic site. So here are the reaction arrows for this reaction. Now you have a protonated alcohol, which is a good leaving group, and having the base in the second step, say sodium methoxide again, then sodium methoxide will deprotonate the hydrogen that has a 180-degree relationship between the leaving group, which I'm showing in red, and the acidic hydrogen. So here, this has the right stereochemical relationship as the only product. And in this last section, I wrote out a few questions you might want to ask in office hour. One, is there a relationship between the reaction rate and the type of alkyl halide? Two, can E2 reactions compete with E1 reactions? And C, how is an E2 reaction different from an SN2 reaction? Would you get different products, for example? Okay, that's been organic chemistry in 5 minutes or less. Thanks for tuning in.